Okay, welcome to the problems at the end of Chapter 8, which is on centrifuges in Fundamentals of Particle Technology. This is question 1 of those problems, and it's all about centrifuges. This is again using the interactive problems to highlight the question rather than doing it all on the Microsoft whiteboard, because there'd be a lot of toing and throwing otherwise. So basically I'm using the interactive problems at Particles.org UK to structure the solution here. Okay, so before we look at the questions, let's look a little bit more in detail about what's going on in a centrifugal system. Okay. I could say something about centripetal and centrifugal, but that's for another time. In engineering, we tend to use centrifugal to mean classically what would be a particle moving outwards, or arguably a series of tangential movements which equates to a particle moving outwards, and that's what we call the centrifugal force, which I know is in physics not strictly true. Anyway, let's try this thought experiment. If we just consider what's going on in A, what I've labelled A just here, situation A, it's a measuring cylinder. Not very well drawn, sorry about that. But in the measuring cylinder we have water, and then let's have one relatively large oil drop. Most oils are of lower density than water, so of course that oil drop is highly likely to float. If we choose an oil drop that is definitely lower density than water, it will float. And the reason behind that is, of course, Archimedes' principle. When a body is wholly or partially submerged in a fluid, it experiences an upthrust equal to the weight of the fluid displaced. Okay, so that oil droplet displaces a certain amount of water. The weight of that water it displaces gives you the upthrust on the droplet, and if that upthrust is greater than the weight of the oil drop, then the oil drop will move upwards, whereas clearly for particles more dense than water, they'll move downwards. Okay, so here we have our oil droplet moving upwards in the measuring cylinder. Now, here's the thought process. Supposing we attach a piece of string to the top of the measuring cylinder, and the other end of the piece of string is you holding it, or some pivot. Okay, and then we start to rotate the measuring cylinder and the string around a central point. So you could be just spinning it round and round yourself, or we could do it mechanically. And the question is, in part C just here, what happens to that oil droplet? Remember, it was moving upwards when it was just under gravity. Does it suddenly change direction and move downwards when we start spinning around? No, of course not, because Archimedes' principle is still valid. Okay, the weight of the fluid displaced is still going to be greater than the weight of the oil droplet, so the oil droplet will be moving upwards, or if we're spinning it round and round, it will be moving inwards. So although it's a dispersed phase inside a continuous phase of water, it won't be moving outwards, it will be moving upwards, just as the particle or the droplet was floating or going to float in our system under gravity. Okay, well, I've kind of let the cat out of the bag there. We're talking here about this scenario where the weight is no longer measured courtesy of the acceleration due to gravity, the gravitational acceleration. It becomes what we call the centrifugal acceleration, where r is the radius and omega is the angular velocity, and it's r omega squared. That is the acceleration term. So basically, when operating in a centrifugal field, all we need to do is to exchange g for any of our equations for r omega squared. It's called field forces. G, gravitational field force, centrifugal field force. But the equations, like Stokes' settling equation, we can make that simple substitution, and we will do so in a moment. So this question 8, part 1, is all about an oil droplet that is going to be moving inwards, not outwards, in our centrifugal field. Okay. Well, if we pop back to the actual question itself, which I think, here we go. I would need to make this slightly bigger, I think, to see what the differences are between some of these. Right, this is going back to Stokes' law. So which of these equations is Stokes' law? This equation here has x to the power 3, although it's not very easy to see it. This equation here has x to the power 2, and is of course Stokes' law. So the correct answer is C for which one is Stokes' law. Okay, so correct answer is C. Let's just check first that we've got that right. Good, we have. So that's Stokes' law. Stokes' law tells us that the terminal settling velocity ut is equal to the diameter squared, the density difference between the dispersed phase and the continuous phase, the acceleration due to gravity, okay, that's how it was defined, divided by 18 times the coefficient of dynamic viscosity, what we typically just call viscosity of the fluid. And the answer is C, that is the correct equation. So let's move on. And now what we've done is swap it over to a centrifugal field. Okay, instead of u, which would be dz dt, if we're using z as the height coordinate, we now have dr dt. Okay, and however, instead of g, the acceleration due to gravity, we need r omega squared. It's a straight swap. Here is our centrifugal acceleration for our centrifugal field force rather than the gravitational field force. So the equivalent equation to Stokes' law in a centrifugal field is in fact answer A. It's not dz dt, it's dr dt. We're talking about a radial coordinate now, where r is the radius, or radial position more accurately, and t is time. And you can see an impending problem coming up because we have r on both sides of the equation. This means that we can't simply define a terminal settling velocity because dr dt, if you like, the velocity radially, is going to depend on the radial position. The higher the value of r, the higher the radial position from the origin of the rotation, then the faster the particle will be. It is literally always accelerating the droplet. Let's just check we had the right answer. We did. Okay, so the correct equation is dr dt equals x squared, diameter squared, density difference, the centrifugal acceleration, r omega squared, over 18 times by the viscosity. So let's move on. So you can contrast the two equations. The equation on the right, Stokes' law, has no dependency on the position. Ut is a constant because there's no value of height on the right hand side. But that's not true for dr dt. Pardon me. Dr dt depends upon the radial position, so we're going to have to integrate, hence it's been left as a differential. Okay, so that's not a question, that's a statement. Right, here is the problem. The problem is probably better illustrated on the whiteboard. So let's pop over to that. This part of the problem is simply the conversion of a certain number of revolutions per minute into the angular velocity. Now, angular velocity has SI units of seconds to the -1. That's not 5 to the -1, sorry about that, it's seconds to the -1. Why not radians per second, which is kind of what people would normally think? Well, a radian is a dimensionless number. A radian is proportional to the ratio of the circumference to the radius of a circle. So it is a dimensionless number, the radian. So angular velocity has the units of seconds to the -1. Okay, and if you remember, we're talking about the centrifugal acceleration being r omega squared. So that would be, r would be in the units of meters, and then omega squared is, of course, seconds, would become seconds to the -2, which is, of course, acceleration, just the same as g. When g, we had meters per second, the acceleration of meters per second, length times by time to the -2. Okay, so we're told in the question that the centrifuge is rotating around at 1,000 revolutions per minute, and we need to convert that into radians per second. So that's 1,000 revolutions. We need to multiply by 2 pi, because each revolution is 2 pi radians, but we also need to divide through by 60, because it was 1,000 revolutions per minute, and we need radians per second, or per second, as the unit. So going back to my trusty old calculator here, we have 2,000 times by 3.14 divided by 60 equals to three significant figures, 105. So that's 105 seconds to the -1. Okay, that's our conversion into radians per second. So if we go back to the website, the angular velocity of the channel is 105 seconds. This is a channel that's rotating round and round. There's an oil drop, which is illustrated in a cutout just here that has the field force on it and the drag force on it. The droplet, you'll notice, is moving inwards. There's an arrow there pointing inwards, and of course if it's moving in one direction, there's a drag force in the opposite direction. So essentially we're using Stokes' drag to oppose the body force inwards, which in this case is the weight, or mass rather, of the droplet times by r omega squared. It's analogous to Stokes. Okay, so that oil drop is moving inwards for the same reason that I tried to explain at the start of this video. So eventually that droplet will hit the inner surface and be removed in the sample tube. And what this question is building up to is the time taken to remove all droplets in this greyed out channel, okay, where the oil emulsion is present, to remove oil droplets of 10 microns in size. So to start with, this greyed out section just here contains droplets that include 10 micron drops, but as time goes on and the tube is rotated round and round and round at 105 seconds to the -1, the 10 micron drops will all migrate to the inner surface and be taken away by the sample tube. Okay, so we said 105 seconds, radians per second, or really seconds to the -1. So let's just check that that's the correct answer. It is. That's good. So let's move on. Okay, so here's our circle channel rotating at 1,000 rpm. The diameter of the outer circle, okay, be careful because it's talking here about diameter. The diameter of the outer circle, so this is from one side to the other side, is 30 centimeters, and the distance between the walls is 2.5 centimeters. So the distance between the two walls of the grey channel here is 2.5 centimeters, and of course the radius to the outer wall is 15 centimeters, not 30, because 30 is the diameter. Okay. If the oil is less dense than the surrounding water, an oil droplet will travel inwards on the application of a centrifugal field force, just as oil floats in a gravitational field. That's good. We now need to integrate the centrifugal rate expression with respect to time and radial distances, and the upper limit for the integration of radial position is, well, think about this, the upper limit, because we're integrating from the outer wall to the inner wall, so the upper limit is actually going to be 12.5. That's the 15 centimeters radial position to the outer wall, stepping back 2.5 centimeters, because that's what we know the thickness of the channel is. So the inner radius is at 12.5 centimeters, the outer radius is at 15 centimeters. So the upper limit, when we come to do the integration, which you'll see in a moment, is going to be 12.5 centimeters, which is correct. Okay, that's important, because if you get the limits the wrong way around, you'll get negative time. I'll illustrate that in a moment. Okay, now here comes the question. This is the equation we need to integrate. We know the upper limit is 12.5 for the radial position. The lower limit would be 15. That's because we're looking for the removal of drops, all the drops between the outer radius and the inner radius. So they're all going to be, the last drops to be removed from the system will be the ones that sit initially at that outer radius and take the time to travel across and to get into the sample tube. I think we need the whiteboard to take this further. So there is the outer radius, which is, there is the outer radius, R0, which is equal to 15 centimeters. That's half the diameter of the device. The inner radius, which I've called Ri, is at 12.5 centimeters. And we're interested in removing all the drops of 10 micron size and above, but the ones of interest will be the ones that start their travel at the outer radius and get to the inner radius. How long does it take for them to move that distance of 2.5 centimeters? That's essentially what we're saying here. Okay, well, there's the equation. We've separated the variables. Clearly we've had to bring R down here and taken dt over here, and then obviously we've taken all the constants out and put them onto the radius side. So viscosity of the fluid, that's a constant. Drop size, that's a constant, 10 microns. Density difference, and that is the density of the dispersed phase. That's important. If you get that wrong, again, you'll get a minus time. So that's the density of the dispersed phase minus the density of the continuous phase. So that's our oil density, that's our water density, and that is the angular velocity, the 105 seconds to the -1. So all we need to do now is to introduce limits that we're integrating over, and we're not going to integrate the constants, they can come out of the integration, and that will be t equals 0. That's the start of the process, and that is of course the time that we're integrating to. This will of course just integrate to t, nice and simple. Now at t equals 0 we're interested in R equals 15, because we're interested in all the drops moving inwards from 15 centimeters to R equals 12.5. That's the upper limit that was talked about a few seconds ago. Okay, right, well clearly what that is going to integrate to is an equation that says T equals 18 mu x squared rho s minus rho omega squared, and that will become natural log, and again get this the right way around, 12.5 divided by 15. And now you can probably see why I wasn't too bothered about potential for mixing units, because this is going to be dimensionless. Whatever factor you want to bring in here to convert it to your favourite set of units will cancel out because it's on the top and bottom. So if you're dividing by 100 to take it to metres, doesn't matter. So we can leave it as 12.5 and 15. Fine. And that will give us the time taken for the process. So let's kick up Excel. All right. It's probably better if I bring that over here so I don't lose the equation. Well, not in its entirety anyway. So I've pre-programmed Excel with the drop size, 10 microns. That's in SI units. The angular velocity is 105 to 3 significant figures. The dispersed phase density is 800. Continuous phase density 1000. And the viscosity 10 to the minus 3 pascals. So the constants are all equal to, not 1, that's a placeholder. I left that open to just to illustrate doing the calculation. So we need x squared, so we want to change that to equals the diameter squared times by the density difference, so we need brackets, the density of the dispersed phase, which is 800, minus the density of the continuous phase, which is 1000, close the brackets, then times by the angular velocity squared, times by the angular velocity squared. Then we need to divide that by 18 times by the coefficient of viscosity. And that, close the brackets, gives us that value. So here is our collection of constants. It's actually the other way up compared to what's written on the right, because I hadn't taken it to the other side of the equation at this stage. But you'll notice, importantly, it's got a negative sign. I like that. That negative sign is useful because I haven't done the ln r1 over r2, or the which will be equal to ln 12.5, whoops, 12.5, that's better, divided by 15, which also gives us a negative number. So there are two negative numbers there, which of course gives us a positive. The positive is 15, or 14.98, it's 15 seconds to 3 significant figures. So going back to problem here, the answer is A, it's 15 seconds. Having got the correct limits sorted out. Quick check, yep, that's right. So it takes 15 seconds for all drops 10 microns and above in size to move into the sample tube from this emulsion that exists between a radius of 12.5 centimetres and 15 centimetres. After 15 seconds, there's no further oil drops of the size bigger than 10 microns in that rotating channel. Okay, just a quick check, 15 seconds is right. I think we're finished. So, thank you very much. Goodbye.